American Railway Signals Principal Practices, Chapter 11, Non-Coded Alternating Current Tracks, and we're halfway through it. Alright. Application track circuit formula example. Applying the formula 9 and 9 tenths to the usual track circuit arrangement considered with the first team of the road using the main type of the relay, and second the electrical road using the main type of the relay having different characteristics. Both these relays are to the element type of the example that may be considered with the representative of the calculation track circuit employment with a single element relay would be made exactly in the same manner. The calculation diagram is used with the case of the two element relay discontinued after the track of the volt, amperes, and power factor, and the transformer is determined for the one winding used in the case of the single element relay model 15AC, the main type track relay. See the vector diagram, figure 24. Steam road of 130-pound rail to 39 feet long, bonded with the railhead, welded bronze strand bonds of the track circuit of 5,000 feet long with the END end fed with the base ballast resistant for 3 ohms per 1,000 feet. The railway track of the 5 tenths of a volt or 5 tenths of an ampere at 0.906 pf on 60 cycles. Local 110 volts at the 0.4400 of an ampere, 0.475 thousandths for the PF on a 60 cycle ideal phase relation for the track lag locals with the voltage 97 degrees. The real impedance of the Z equals 5 times 0.2 tenths of A equals to 1 ohm at 0.36 PF. In table 1, ballast conductance at G equals 5 times 1 times 1/3 is equal to 1.667 MOH is 1 PF. The relay transformer lead tracks 150 feet, numbered to 6 copper wires for each of the set of the 1200s of an ohm. Voltage drop the relay end leads to 0.5 at 1200s of an ohm. There was 0.600 of a volt. Rail voltage relay ends with the 0.500 of and plus 0.600 of a volt equals to 555 thousandths of a volt. Each E is equal to 0.55 thousandths of a volt, 500ths of a volt, 5 tenths of a volt, 463 hundredths of a thousandths of a volt, 0 plus 139 thousandths of a volt, plus 0.64 thousand volts, etc. 1.3 volts, and the I is equal to 1.78 amperes. Relay voltage opposite relay of the 0 is equal to the 555 thousandths of a volt obtained with the figure of 24. With the adding vertically with the relay voltage ER with the 5 tenths of a volt relay lead voltage drop at the 0.600 of the volt, later being the phase within the heads of the parallel with the relay current with the I is equal to 0.500 ampere, which is drawn with the angle of the PF of the 0.906 is the cosine of the angle of the lagging of the relay volts for the ER. The PF is shown above with the track element relay and plotting the various leakage of the current, therein corresponding with the voltage drop in figure 24. Remember, referring to the equation of the 9 for each of the term of the value voltage series obtained with the multiplication proceeding with the term in the current series with the multiple rail impedance of the G. The power factor of the G is 0.36. Hence, each of the term of the voltage series and leading with the leading angle whose PF is 0.36. Using the preceding term of the current series for the base of the lines of the referring to the equation in each of the term equation 10, each of the term current series is obtained with the multiplication proceeding with the term in the voltage series submultiple with the ballast conductance of the G. G is being non-inductive with a PF of 1, and hence for each of the term of the current series laid off parallel with the preceding term in the voltage series which produces it. Alright, following the above method, current for the transformer end of the track circuit is found with the edge to be I of the 1.7 amperes. This would be the vector sum of the relay current with the various ballast leakage current laid off due to the attention phase relationship. Likewise, the voltage of the rail at the transformer end of the track circuit is equal to E at 1.3 volts, and being vector sum of the relay voltage, the various relay voltage drop is caused with the ballast leak currents. To prevent the low flow of the injurious short circuit current through the transformer secondary with the track circuit is necessary to insert the sum of the current light limiting devices being the transformer and the track in order to obtain the maximum power economy for the track circuit arrangement at track. This shows figure 24 shows the vector of the track circuit using a model 15 relay. Up here is track 15, and this is a whole bunch of different angles of relays and volts. Reactors are shown in figure 25. The use of the presence of the track resistor from the taps available on the reactor once selected with the volt drop until combined with the voltage track leads at the transformer end with the result with the transformer secondary voltage ET approximately double the rail voltage E at the transformer and in this case 0.7 ohms taps is shown. This is the adjustable track reactor. Selected with the voltage drop of the reactor within 1.7 amperes flowing through with 1.78 times 0.75 is equal to 1.335 volts. The vector is laid off with a PF of 0.2 tenths within the current as the I as the base. Transformer current 1.78 flowing through the leads between the transformer and the track gives the voltage dropper 1.78 times 0.112 equal to 0.214 volts laid off parallel with the current since the leads are non-inductive. The resulting value of the transformer secondary voltage ET with the current I or the values required to obtain the voltage E with the current I with the delivered relay with the phase relations between the two elements for the relay ideal with the ideal phase relation for the relay as listed previously occurred with the current in the track element lags and voltage local elements of 97 degrees. Thence there is practically no change in the phase between the secondary and primary of the track transformers and since the primary of the track transformer is fed from the same source of the power supply local element of the relay consequently the phase is the same. The phase difference between the track and local elements of the relay may be obtained measuring the angle between the track transformer and secondary voltage ET with the relay current I with the vector diagram. The measured of the angle the 87 difference of 10 degrees from the ideal range angle of 97 degrees in order to compensate the difference between the measured ideal phase relation of the track transformer secondary voltage ET with the current I must be increased. The ratio by which these values must be increased is ET over cosine of 10 degrees and I over cosine of 10 degrees resulting of the following. A corrected of 2.64 volts and an I of corrected at 1.81 amperes. Another method of correcting the transformer selected voltage and current, the use of the curve shown in figure 62 of the chapter 10 of alternating current relays. Instead of the reactor using the resistance until they have the unit power factor that has been used with the greater angle, the difference the ideal would require greater corrective voltage of the current supply value for the greater power input. The angle between the transformer and secondary voltage ET and the current I may be scaled from a vector diagram with the cosine of the angle or PF of 0.63, hence for the total power of the track and circuit is unoccupied. The ET corrected times the I corrected equal times the PF is equal to 2.64 times 1.81 times 0.63 or 3.01 watts. When a train leaves occupying the track circuit with the opposite of the transformer, the current of the flowing the equal of the corrective of the transformer secondary voltage divided in the vertical sum of the inserted resistance to resistance of the transformer track leads the voltage drop of the parts of the circuit is sealed in the diagram of 1.39 volts with the due to the current of the 1.78 amperes I and hence the combined impedance value of the reactor leads is Z equals equal to 1.39 over 1.78 or is equal to 0.78 ohms. When the train of the track circuit is above, there will be only 0.78 ohms in the series where the transformer secondary neglecting and comparative small resistance of the wheel and axles of the train. The short circuit current flow will be 2.64 over 0.78, which equals to 3.385 amperes. The corresponding power factor is 0.34 scaled. The diagram being of the power factor of the voltage drop of the reactor leads with respect to the transformer current I. Therefore, the total power with the block occupied with the 2.64 times 3.3385 times 0.34 is 3.04 watts. The style PTV 42 alternating current vane type of the track relay. See the vector diagram, figure 6. Electric road, 100 pounds, 39 feet long, bounded to the capacity track circuit with a 4,000 feet long end fed with a ballast resistance 3 ohms per 1,000 feet. Relay track of the 0.34 volts to 0.84 amperes, 0.407 pfs, and on cycle local 115 volts of 0.165 amperes and 0.358 pfs on a 60 cycle ideal phase relation track voltage leads local voltage 90 degrees. Rail impedance for the Z 4 equals 4 times 0.21 equals 0.84 ohms at the 0.3 tenths of PFH and see table 1. Ballast conductance CG is equal to 4 times 1.3 equal to 1.33 MHOs at the P1 PF. Impedance bond at each of them the track circuit of 1,000 amperes. The direct current for the propulsion current of the relay unbalanced in capacity of 270 amperes. Impedance for the 60 cycle of 0.5 ohms at the two PFs. Relay and transformer lead track of the minus 150 feet and the number of copper wires for each of the set of the 1200s for the ohm. Voltage drop relay is 0.8400 for the times 1200 to the 101 thousandths of a volt. The voltage at the E at the relay end is 0.34 times 0.104 equal to 0.393 volts. Our bonded current relay at 0 end is equal to 0.39 volts divided by 0.5 by 5 tenths is equal to 0.786 amperes at the tenth of the PF. Total current in the at the IE relay end is 8.4 plus 0.786 equals 1.58 amperes. E is equal to 1.905 volts, and I is equal to 2.38 amperes. Referring to figure 26 of the relay voltage of the ER with the 0 at 3400 for the relay current with the IR 8400 for the relay off at PF at 407 thousandths of the previous example, taking into account with the voltage drop relays at 101,000 volt laid off the parallel to the relay current with the relay voltage end of the track circuit of the found to be 393 volts is 393 thousandths of a volt. The voltage of the current through the impedance bond at the A at the relay of 393,000 volt times divided by 5 tenths is equals to 0.786 thousandths of a volt ampere laid off the lagging angle and the corresponding at the 0.25 PF with the rail voltage E 0.393 volts of the total current with the relay end of the track circuit vertical sum of the relay current with the bond current equals 0.84 plus 0.786 equals 1.58 amperes equaling to I. Applying the formula of 9 to 10, laying off the various ballast, leakage, and currents of the voltage listed above the same manner as the previous diagram, the figure 24, the voltage current value of the rail opposite of the track transformer found E is equal to 1.905 volts, the I is equal to 2.38 amperes. The voltage applied with the impedance of the bond with the transformer and with the current through the bond is equal to 1.905 divided by 5 tenths is equal to 3.81 amperes, which was the lead with the lagging angle corresponding to 0.2 PF within the E with the total current IT fed with the track measured at 6.01 amperes. Being vertical sum of the track current I is equal to 2.3 amperes with the impedance of the bond current with 3.81 amperes for a great power of the economy in the case of the resistor unit is used instead of the reactor selecting the tap of the track transformer secondary voltage ET with is approximately double the rail of the voltage E with the resistor tap of the 0.33 ohms is selected, which with combined with the lead resistance of the 0.12 voltage drop with the combined resistance of equal to 6.01 times 0.45 is equal to 2.7 volts laid off parallel to the current vector IT with the track transformer secondary voltage ET measures 3.87 volts. Before the ideal relations between the relay voltage of ER leads to the local voltage of ET 90 degrees. For the vector diagram, measure the angle between the relay voltage of ER. Local voltage of ET is 32.5 degrees. The phase difference between the ideal actual conditions of 90 degree minus 32.5 degrees is 57.5 degrees. Compensation of the track transformer secondary voltage ET and the IT is obtained by the following. The ET corrected is equal to the ET divided by the cosine of 57.5 degrees. IT is corrected by the IT of the cosine of 57.5 degrees, equaling the ET is equal to 72 volts. IT is 11.2 amperes. With the track circuit, the total power of the ET corrected with the IT corrected with the time the PF of the 11.2 times 0.859 is equal to 72.2 watts for the power factor of 0.895 being the cosine of the angle between the ET and IT as scaled by the diagram. With the train occupying the track circuit opposite of the transformer, the maximum current is equal to the transformer volt ET divided by the total resistance between the transformer and the track equals 7.2 divided by 0.45 equals 16 amperes at 1 point PF. Since the resistance is not inductive of the power, will the track circuit is occupied as 7.2 times 16 times 1 is equal to 115.2 watts. The apparent that the reactor instead of the resistance unit has been used in currently emitting devices between the rails and track transformers. The difference with the phase angle have been greater than the 5.57 degrees found above in the relay would not have the operable due to the imperfect phase and displacement. The train shunt. The general alternating current track relays have much lower internal impedance of the ordinary track relays. Direct current practices. For the example, the Model 15 vane relay, which was considered with the connection to Figure 1224, has impedance with the Z equals 20 the Z equals E over I, and ZR equals ER over I, or equals 0.5, 0.5, or 1 ohm, while the PTV is 42 vane relay discussed in connection 50 with Figure 26 as an impedance of 0.34 over 0.84, which gives it 0.405 ohms as compared to the resistance of 4 ohms of the standard direct current relays. Since the two circuits of the parallels are encased with the track relay, this shows another car wheel across the rails, but the current in each of the circuit inversely proportional resistance of the track and flows with the train shunt of the given resistance alternating current track relay with all the large proportional current through that would be case with the direct current with the relay. Hence, the train shunt is not so effective in the former case. Alright, figure 26 shows the vertical track circuit of the using PTV diagrams. Here's the track circuit. It shows all your different tangents and volts, opposite transformers, and degrees. Just we're using cosines. I really don't get that, but the value of the train in ohms of the course is equal to the impedance of the axle vertically with the ohmnetic contact resistance between the rails and the car wheels. Impedance for the wheel axle part of the shunt circuit is negligible, but hence with the reaction factor to the in the circuit may be also neglected. It is also true that the case of a heavy rolling stack within play with the seam in the electrical trunks line surface of the wheel relay contact resistance may likewise considerably insufficient. With the table 3 was complied with a series of tests made on the rails with clean bearing surfaces in which the single pair of the wheels, therefore axles, submitted to the various loads. It will be noted that the total resistance of the shunt, therefore, formerly particularly independent of the loading, while the total shunt resistance is extremely low in all cases. It might be noted that, as might be expected, the total apparent resistance increases the frequency compared to any of these shunts resistance. The impedancy of the relays be given an enormously high due that the shunt may be considered practically imperfect. Table 3 shows the contact of the surface of the wheels and rails can be clean metal. Frequencies at 25 and 60 cycles in DC. Number of tests 1 through 4 and 40 cycles with the total weight of the track, the amps axle current, volts across the rail, and ampere metric resistance between the rails and V of the wheels and axle. And then 60 and DC have 3 tests on them in the same other values. It's only when rusty and dirty rails with the surface encountered with the resistance of the train shunt becomes significant. The same is applied for the equally well the direct current of the track surface. Every single man is familiar with occasional difficulties experienced the heaviness sanded with the track of the table 4, with the indicates what the surface of contact resistance may amount to. The test having been made on a 4-wheel truck loading on the total weight of the rails was 40,900 pounds. Table 4, total amperes through the axle volts across the rails and train shunts in the ohms are shown in clean rails at 25 cycles and 60 cycles, and rusty rails at 25 and 60 cycles. On steam and electrical trunk lines with the rolling stock generally heavy, the strain movements are frequently enough to keep the railway clean. It may be safely assumed that the train shunt resistance is extremely low as to be negligible. On some of the intern or urban trolley, however, where the light signal car trains operative movement, there are not frequently enough to keep the rails bright. The value of the train shunt may be taken into the consideration in such a case that it had been found not to run much higher than the values of table 4, since the relay shall be shunted out of the point of at least 50% and below. A minimum shunt point is often customary to make an electrical road track circuit shunt calculation with the train shunt value of 0.06 ohms. In this case, the electrical road with the train shunt may be comparatively high resistance due to the light rolling stock of rusty rails resulting from the infrequently trained surface and thoroughly generally advisable to check with the track circuit calculation described in the following in order to certain the relay will be shunted upon the opening with the train blocking surface. Not always. This is a note somebody copied on there. I don't know what it is. It's star. Method of controlling track circuit shunting is sensitive. The track shunt is less effective when the train is opposite of the relay. The train of the entire railway impedance will be circuited between the train shunt and the track transformer will result with the track feed for the current, but the current consequent will drop with the resistance impedance between the transformer and the track will be less than the train opposite of the transformer. Since the voltage rail opposite of the transformer is vertical difference between the transformer voltage drop and the resistance and the reactance inserted between the transformer and the track, it follows the train opposite with the relay of the voltage of the track opposite with the transformer in terms of the opposite relay with the greatest when the train is in relay end of the track circuit since the later with the worst condition encountered with the calculation to prove the effectiveness of the track circuit should be made in the basis. It is desirable to reduce the lowest point of the possible with the voltage relay with the train in the block will be apparent with from foregoing where the impedance of the resistance as the case may be is inserted between the transformer and the track, thereby verifying the effect of the controlling of the voltage of the railway opposite of the transformer. Since the voltage decrease, so also will the voltage of the release decrease. Hence, the impedance of the resistance of the high value of the short circuit current with the train of the block will cause the corresponding heavy drop between the transformer and the track. As the result of the voltage opposite both the transformer and relay will be low. It is customary with a sufficient high impedancy of the resistance so that it will be with the block of the clear and the voltage of the track opposite with the transformer will be 1/2 of the transformer secondary, and it was with the train shunt in mind. It says the star is not valid. The arrow has the I can't read that. That these values were employed with the connection of figure for 24 and 26 with such adjustment with the track voltage generally fall perfectly safe with the figure with the train comes into the track circuit inserting dependence with the resistance for the given the transformer voltage greater than twice the track voltage will very rarely be justified since there are after the relay is once shunted with a large margin on the safety and a further increase of the inserted but the impedance resistance will only result with the useless of waste of power. Whether with the aid of the vector diagram shown in figure 24 and 26, it is not of the difficult matter to the association with whether the inserted impedance of the resistance determined at the base of the transformer volts being the twice of the track of the volts with the block unoccupied will ensure the front of the contact with the track relay open with the train opposite it assume over the course of that all the track circuit with the contents are known, including the shunt point as well as the normal operating point of the relay of the train shunt given the value across the rails at the relay with the normal operating voltage relay poses the drop in the track leads to the first term the E of the equation 9 with the consideration train shunting as impedance bonding with the unity power factor construction diagram like in figure 26 leaving the proportional bonds out of the same road track circuit is being investigated. In the case of the electrical road circuit in the train shunt it will be simply constituting an extra bond at the relay end of the multiplying the proportional bond. The vector diagram is obtained with the course of the indicated with the transfer voltage considerably greater than the actual extent of the determined with the calculation with the block clear calling the hypothetical transformer the voltage ETS of the actual extent with the transformer voltage ET is at the voltage relay end of the block must be reduced to the proportion of ET over ETS in the turn of the relay voltage current will decrease in like the ratio if the reduction is found if the relay current was below the shunting of the portion of the instrument the impedance of the resistance shows from the block clear of the condition but considering the satisfactory with the reductions of the non-sufficient impedance with the resistance inserted between the transformer and the track will have to be arbitrarily increased until the calculation proves the relay is effective and shunted. Power fraction triangle. The laying out of the vertical circuit of the diagram is shown in the figure 24 with the 26 the value of the various angles are given with the calculation in terms of the cosines of their being of the power and the factor considering the angle of these places spacing of the vectors therefore much more than effective through the use of the triangle marked with the cosine, such as the shown in figure 27, then through employment of the power tracking indicated with the degrees, since the later case of the angles correspond with the cosine would have to be locked up into the table. The transparent triangle should be used, as it is often necessary to use the upside down with lines of 0/10 and to 0/7 as drawn with the vertex A laid off with the protractor of the angles with the baseline BC with the corresponding with the cosine 0/10, 0/1/10 and 0/7 as the given with the standard cosine table to 0 lines 0/8 of a tenth to 0.99 hundredth as drawn with the vertical B and laid off with the baseline BC lines. Likewise, at the angles corresponding with the cosines 1/8 of a tenth to 99 hundredth, the considerable care should be exercised using the triangle at first, especially when reversing it. And otherwise, one way may be using the complementing the angles instead of the angles itself. Figure 27 shows the power factor triangle in the construction of the track circuit vector diagrams. This goes from B to 7 and 1 to 7, B to C, and 0.99 to 0.8 tenths of A to C. Non-coded alternating current track of the circuit should be maintained with the testing in accordance with the single section Association American Railroad instructions as follows. Adjustment of alternating current track of the circuit depends on many of the factors such as the type of the track circuit, whether double the single rail with the steam of the electrical traction, length of the track circuit of the belt, condition desired, the shunting volt value of the both relay and the transformer, end of the track of the circuit, the type of the relay with the weight of the train equipment. 2. When the marking of the train shunt resistance of the test should be made in accordance with the form 7003 in Figure 28. For the more single element relay, the voltage of the relay track terminals under the wet belts, other adverse conditions must be at least 10% of the higher than the values given on the manufacturer's tag nameplate of the taking care of the varying ballast and bonding. The 2-element relay, the voltage of the relay track terminals under the wet ballast and other adverse conditions should be at least 10% higher than necessary to energize the relay with the normal portion in front of the contact compression on one of the account of the various phasing of the conditions with the necessary voltage of the track element with the consideration excessive with the voltage values most marked on the manufacturer's tag and the nameplate and check with the power of the voltage applied with the cross of the track terminals of the relay under the wet and other unvariable conditions. It is to shunt the relay so that it contacts open half of the remove of the shunt and the contacts come up at the front stop, sufficient energy passing in the track windings. Figure 28 shows the train shunt resistant testing. It shows the equipment circuit and the rail surface condition, kind, initial numbered weight, wheel surface testing number VA and VAR, one axle, two axle, and entire equipment and equipment moving in test number 2. Alright, full voltage of the relay. Local terms must not be necessary or possible. The normal voltage given the manufacturer's tag when name plate is less than the normal value of the impressed with the across. For local terms, more energy will have to be used from the track element to cause the proper operation, except for the central frequency relay. The reduction of local voltage of the central frequency relay in general goes down to the required with the additional energy with the track element of the reduction of the local voltage should be avoided, but it tends to be increased with the time of the shunt. 5. When shunting 2-element track relay, shunts must be applied with the terminals of the track element, not local element. 6. On steam road circuits with the voltage of the railway transformer and should not be more than one half of the transformer secondary under the worst of the track conditions where the rectifying of the transformer are in use. The voltage on the railway at the transformer end should not be more than one half of the open circuit of the transformer and the secondary voltage. 7. On electrical road tracks, obtaining the adequate broken rail protection necessary to be making the adjustment so that the under worst track condition of the voltage rail opposite of the transformer and 2/3 of the transformer secondary with the active transformer are in the use of the voltage on the rails of the transformer should not be more than 2/3 of the open circuit transformer secondary voltage. Phase angle measurement to obtain the phase operation 2-element track relays under the diverse ballast condition. The phasing the measuring instrument should be used to determine the phase angle relations with the relay approach with the ideal value. These measurements may indicate the adjustment should be made to improve the phase relationship. 9. Circuit control. Switch control. Circuit controllers must be maintained and tested in accordance with the instruction of the switch circuit controllers. Ballast resistance and rail impedance of the ballast resistance should be kept as high as possible, keeping the ballast free from the rail with the rail fastening provided with the proper drainage. The broken track spikes must be driven in through them through the ties. Bonding of the men must be installed, maintained in condition to ensure the low resistance bolts and the ankle bars should be kept tight with the alternating current. The track circuit test must be made in accordance with the AC track characteristics. Resistance of the rails bonding with 1,000 feet of the track which shall not exceed the assigned value of the particular type of the bonding employed. Resistance of the ballast per 1,000 feet of the track should be preferably not less than 2 ohms when wet, and 15 bonding of the track circuit connection. 15 bonding of the track circuit connection must be inspected, instructed and renewed when necessary. Switching frogs must be so bonded when removed the track circuit will be open. 17. When fastening the shunt wire, the track circuit connections care must be taken so that the staples do not ground. The circuit of the staples wires must be kept in place in good condition. 18. The following of the circuits must be maintained to avoid breaks and undue resistance. 19. The cross bonding of the electrical propulsion roads. To obtain broken rail detection is desirable for the cross bonding between the neutral connection for the impedance of the line of the parallel tracks between the neutral connection. Negative propulsion return cables should not be located to closer than alternating impedance bonding. Location calculation should be made with checking by field tests under the most adverse conditions so that the cross bonding with the install does not interfere with the desired broken rail detection. 20. The both rail the double rail traction circuit should be equal with the bonded because of the defective bonding in the one with the rail will cause the unbalanced condition of the track circuit in unequal amounts of return the propulsion for the current in the 2 rails. When the direct current propulsion current propulsion double rail track circuit in an unbalanced propulsion current may saturate the iron core with the impedance of the bond and lower the bond of the impedance with such a point with the track of the relay may be shunted. B. The alternating current propulsion double railway track circuit unbalance. The proper propulsion conclusion will cause the impedance of the bond to act as an auto transformer. Single the track relay is connected with the multiple with the bond and auto transformer. The voltage may be cause sufficient as alternating current for the propulsion frequency to flow the relay to cause the opening with the contacts of blow of the protective fuses. Insulated rail joints. 21. Insulated rail joints must be maintained and tested in accordance with the instruction of insulated rail joints. 22. Broken down insulated rail joint protection when two elements of the track relays are used. Polarities of the adjacent track circuit must be staggered within the signal to keep the clear of the position. 26. The resistor. When a single rail of the circuit is used, the electrical roads of the carrier must be taken with just the resistor of the relay transformer in so that the amount of the propulsion current permitted to flow through the relay track winding is less than the amount specified with the given relay. That with a heavy direct current, where heavy direct current propulsion is present, the shielding of the balancing and impedance may be also installed with the connection with the track relay, protecting against the direct current relay windings. Reactor. 24. The current limiting device for the use of the transformer to track the lead should be the reactor. If possible, the lead looses and a reactor less of the resistor. The resistor placed with the reactor should be used only when required to directly phase the relationship with the two-element track relays to protect the relay and transformers from the propulsion and return current. Fuses. The fuses may be inspected with the instruction but replaced in the kind when necessary. 26. Relays must be maintained and tested in accordance with the instruction. Alternating current relays. 27. Testing. In testing alternating current track circuits, it is not possible to obtain the relay with the current with simply interest of the ammeter between the relay and the track, since the resistance of the alternating current ammeter is high that they considerably reduce the current through the relay when inserted to measure the current relay with receiving the track current. Measure the first voltage across the relay track terminals. Insert the ammeter with the truck leads again with the measuring of the terminal voltage. The voltage is divided by the current that gives the impedance of the relay, which corresponds with the resistance of the direct current relay with the divided relay terminal voltage read with the ammeter removed, and the impedance of the relay current will be obtained. 28. Ground resistance testing must be made in accordance with the instructional resistance made grounds. 29. Shunt sensitivity. Shunt sensitivity test for the track circuit is made with determining the maximum resistance that can be placed across the rail opposite of the relay and opposite of the transformer to cause the relay to contacts to open. The resistance is less than 0.0600 of the ohm, and corrective measures must be taken at once. 15 feet of the number 16 AWG gauge. A copper wire has a resistance of 600 ohms. Shunting testing must be made as follows. Determine switch point side insulated joints of the lead rails at the end of each of the following circuits. The crossover switch points and insulated joints of the lead rails of both sides of the insulated joints at the center of the cut are also over the center, and the insulated joints are not used. Make tests as specified in instruction 30A. 31. Shunt testing must be made during the drying weathering conditions when the maximum current is flowing through the relay coils. And 32. Top of the rails should be kept free from the sand and rust and other foreign matter that affects the proper shunting of the track circuits. 33. If shunting of the sensitivity track circuit is lower than the similar track circuit tracked against for the following of the possible causes of the improper amount of lighting, limiting impedance of the resistance between the transformer and the track, between the track relay and track and the relay. B. The excessive energization of the relay under the minimum of the ballast resistance. And C. The defective sluggish relay. General 34. When a track other than conditions are such that they may cause signal interruption or unsatisfactory operation, signal apparatus for the person immediately responsible must be requested to correct the condition. If such a request is not acted upon with a reasonable time, but the matter must be reported with the proper authority providing. 35. Wire and cable must be maintained handled in accordance with the instruction of wire and cable. 36. The lighting and arrestor must be properly connected and maintained. 37. The pipeline under the rail must be clear base of the rail, at least 1.5 inches. If the track circuit fails to operate and properly, check the following possible causes: the broken rail, loose condition, defective bonding, defects in insulated rail joints, defects in switch rod gauge point, pipeline insulation, low ballast resistance. 39. Extreme change of the pipe must be made in the track circuit to accept the permission of the proper authorities. 40. Any unusual occurrence development in track circuits must be properly reported to proper authority. Are precautions to be observed with the taking and the reading of the field with the real impedance of the available for resistance? 1. Insulated joints should be tested with an ensure that there is no leakage through them, that they can be easily done by the shunting of the track circuit on the other side of the joints, noting that the cause no changing of the reading of the ammeter in the transformer leads. 2. Bonding should be tested and taken voltage readings across the track at every 15 rail lengths. They require the special length of the track circuit. That the track circuit is normal operating condition. The poor bonding of the ballast will be indicated with the unusual voltage drop between the successive readings. It should be noted that that if there are any of the poor conditions by the select sections of ballast and bonding of the track circuits, which would be made to distribution leakage non-uniform, also given the erratic voltage reading of the unusual voltage drop is found to be between successive readings and taking the reading across the rails every rail length. At the same time, inspecting individual bond wires of the particular section while the steps will be unusual and enable the defective bond to be detected. 3. The set of readings first with the relay disconnected the second with the track short-circuited, but it should be taken if possible without the intervening of the train movement through the track circuit wall, which might change the conditions of the bonding insulated joint. 4. The jumper indicated with the figure 29, the short circuit of the track relay with the end should not have a higher resistance than 5 feet to the number 8. Number 9, AWG gauge, AWG hopper wire is connected with the rails for by use of lower resistance testing clamp. 5. The resistance of the voltmeter should not be less than 20 ohms per volt in case of the desired measure for the rail impedance of the ballast resistance of the double rail electric railroad circuit is necessary to disconnect the impedance of bond between them taking the readings. Alright, this is for formula calculating rail impedance of ballast resistant AC track figure C, figure 2930. Disconnect impedance bonds, if any, in relay. Observed readings EO equals volts across the rails, opposite transformer tracks open circuited. ES volts across the rails, opposite transformer track circuited, circuited opposite. Track relay IO, amperage of the track of the transformer track open circuit. IS, amperage of the track transformer track short circuited open opposite. Relay EOV4 volts across the rail at 0.4 length of the track surface of feed end the calculated values. ZO is equal to EO over IO, impedance of the track circuit that open circuit, and ZS is equal to ES over IS, impedance of the track circuit and short circuit opposite track relay. And R is equal to EO4 times divided by IO4 track balance resistant track circuit. R is equal to R times the L with the length. L is equal to the length of the track surface, the track circuit in 1,000 feet ballast, and is equal to the ballast of the resistance per 1,000 feet of the track. Z is equal to ZO times ZA divided by R rail impedance per 1,000 feet of the track. And then we got a little sign with a circle and through a slash through it equal the phase of the angle of the rail impedance that can be obtained directly from the curve of the track, or figure 30, taking the value of the corresponding Z to the particular track circuit frequency. Alright, this shows examples of 55,000 feet of the AC track circuit, frequency 60 cycles, and this just shows figure 29 track circuit connections. This shows, figure 30 shows the curve showing the approximate relationship between rail impedance phase and angle of the rail impedance ohms and per 1,000 feet of the track, the rail angle of the rail impedance in degrees. Or example of typical instruction. The instruction of the adjustment of the 60-cycle alternating current circuit of the steam lines is follows. 1. General 1. The adjustment of the alternating current of the track circuit depends on many of the factors such as the type of the track circuit with the double and single rail with the seam, electrical traction, length of the track circuit of the ballast condition, the desiring the shunt bed of both relay, the transformer ends of the track circuit, the type of the relay, and the weight of the train equipment. 2. The voltage value. The voltage relay with the local terminals must not be as possible. The normal voltage given the manufacturer tag and nameplate unless and if less than the normal voltage value is impressed with across the local terminals, more energy will have to be used for the track element in case of the proper operation, except for the central field frequency relays when a reduction of the local voltage of the central field frequency relay generally does not require additional energy. The track element, the reduction of local voltage should be avoided as it tends to increase the timing shunting. 3. The voltage of relay track terminals will vary for the changes in ballast for the bonding of the resistance. Figure 31, 32, and 33 are the curves showing the minimum, showing the maximum voltage at the relay terminals of the track circuits of 5,000 feet long as the various ballast of resistance, with the minimum of the ballast resistance of the track circuit involved in not less than 405 ohms per 1,000 feet of the track. Figure 34 also gives the curves of the track the circuits of 4,000 and 6,000 feet length, and figure 34, 35, and 36. A similar curves to be used for the minimum ballast resistance of 2 ohms per 1,000 feet of track. 6. It is found to be the best results obtained with the track circuit from 4,000 to 5,500 feet with the length of metal 15 condenser relays with the using a 1.3 ohms with the reactor with the circuit and baking the adjusting of the voltage by using the nearest voltage of the track transformer secondary to give the desired voltage at relay with the transformer secondary does not have the sufficient tap to do this. All the cases may be necessary to higher impedance on the reactor to keep the voltage on proper limits. This shows this is a curve showing the maximum voltage required at the relay track appointment, the volts versus the ballast resistant ohms per 1,000 feet. This shows the ballast resistant ohms per 1,000 feet and voltage. And then we have curve showing the maximum voltage required to relay track element, ballast resistance ohm per 1,000 feet voltage track element. Alright, and then you have ballast resistance ohms per 1,000 feet at voltage curve showing the maximum voltage required for the relay track element. Ballast resistance ohms per 1,000 feet over volts, the curve showing the maximum voltage required for the relay track element. Another ballast resistance ohms per 1,000 feet over volts track elements. Curve showing the maximum voltage required for the relay track element. Alright, ballast resistance. The ballast resistance is the resistant ballast and tide leakage of the current of the one railway circuit to the other. The resistance constantly changing may vary for the very dirty track of the circuit from 2 ohms per 1,000 feet when the wet is 80 to 100 ohms per when frozen. It is a wide variation that makes it difficult to adjust the track circuit to operate with satisfaction with the ballast the wet and not over-energizing the relay of the ballast is dry and frozen. 8. The ballast resistance. 8. To find the actual ballast resistance alternating current track circuit requires the considerable apparatus at any time of the approximate ballast resistance in such a circuit close enough that practical purposes might be determined quite easily. Alright, you have your transformer, your ammeter, the voltmeter, open relays, a local switch. As shown in Figure 37, the insert ammeter the circuit to open the circuit of the track element of the track relay, the voltmeter reading of the track vortex of the wave through the track circuit from the feed end of the reading of the ammeter. The volt should be taken simultaneously practicable at least within a few minutes of each of the without the track being occupied between the readings 10. The formula is taken the ballast reading of the method outlined in instruction in Figure 8 and 9. The RB is the is E over IO, which is where the resistance ballast is. Example, assume the meter is indicated 4.16 volts over and 1.2 amps. The RB would be 4.16 volts over 1.2 amps with 3.47 ohms equal the ballast resistance. The ballast resistance entire circuit of the 3.47 ohms. Here, the ballast resistance per 1,000 feet of the track multiple the ballast resistance in ohms for the entire circuit for the length of the circuit within 1,000 feet. Thus, in the circuit with 499,000 feet long, the ballast resistance per 1,000 feet of the track would be 3.47 times 4.9 or 17 ohms. 11. A test to determine the minimum ballast resistance for each of the track circuit should be during the immediately after the shower late of the winter or the early spring with the ballast when it's wet from melted snow or from thawing. If the track circuit should fail on an account of wet and dirty track, the minimum ballast resistance test should be made at the time the minimum ballast resistance is obtained. To make it necessary to make similar tests, there should be a ballast conditions getting materially better or worse. Alright, your phase angle. To secure the proper efficiency operation, 2 element alternating current relays will require the proper phase displacement between the currents and 2 elements for the relay. This is especially true if the voltage is low on the track element on the relay. 13. The single-phase transmission line is used with the displacement of the phase obtained with the insertion of a resistor, a reactor of resistor both in the circuit of one of the both elements of the relay. The phase displacement is further affected with the impedance of the rail and the ballast resistance of the impedance of the rail, and particularly inconsistent with the bonding of the good condition. The variation of phase displacement due to the change of the ballast resistance greater than dirty track circuit. For example, the 5,000 track circuit with the model 15 vane relay would then be variation of about 40 degrees in the phase of the track element relay of the ballast resistance of the 20 ohms per 1,000 feet of the track. Of circuit having the minimum ballast resistance of the 2 ohms per 1,000 feet, for the sure reliable operation of the relay of the necessary to adjust the phase with the nearly ideal phase relationship existence with the ballast resistance near its minimum. The term of the ideal phase relationship be used with the instruction means of the phase displacement at the relay operating efficiency. 14. The term proper phase relationship is understood to mean that the phase adjustment which with the relay will be properly more efficiently under the low ballast resistance shift far enough from the ideal with the dry or the frozen track conditions to afford some of the protection against the high track voltage. The track circuit adjustment in accordance with the instruction will meet the conditions. Method of adjustment model 15 vane relays find ballast resistance between 1,000 feet of the track outlined with the instruction 8, 9, and 10 that have been previously determined the minimum ballast with the resistance of the circuit and the minimum ballast resistance per 1,000 feet of the track and 4 ohms is better. Consultant with the figure 31 to determine the maximum permissible voltage in the relay terminals of ballast resistance conditions existing. The minimum ballast resistance is less than 4 ohms per 1,000 feet of the track. Figure 34. Connect the reactor so that 1/3 of the ohm of the circuit between the track transformer secondary track of adjusting the voltage on the secondary and give the correct voltage secured by the proper curve. At the terminals of the track element with the track relay as stated with the instruction 3, 4, 5, and 6 that may be necessary to increase the impedance for the reactor with the circuit of the voltage tap within the secondary of the Trck. The impedance for the reactor should be checked with the voltmeter and ammeter to be sure the value is approximately the same as given with the taps used. The very essential for the reactor has adjustable air gaps. 16. The TV30 relays. The produced outline instruction 15A and B and C, except the figure 32 and 35 are used to be used in place of figure 31 and 34. Model 2 from the form A. These positions of an induction motor type relays them before the adjustment of the track voltage producing the outline instructions of the 15A, except the figure 33 and 36 are to be used in place of figure 31 and 34 for connecting the tap reactor between the track transformer tracks so that it is 3 ohms to tap in the circuit of adjusting the voltage of the secondary of the transformer and give the corrected voltage is secured with the proper curve for this type of the relay. At the terminal of the track element of the relay, the check of the impedance of the reactor should be made at the described instruction of 15A. The method of testing approximately 2 low wet ballast resistance. Measure the ballast resistance on the day of the test. Find the total ballast conductancy of the track circuit taking the reciprocal of the tellur's ballast from resistance found in instruction 18A to determine whether the total conductancy divided by the length of the track circuit of thousands of feet by ballast resistance of ohms per 1,000 feet. Subtract actual conductancy instruction 18B from wet weather conductancy in instruction 18C. This will result in giving the additional conductancy which must be added with it, which should be added to distribution in 2 parts along with the track circuit as indicated in the following table. Table for the distribution ballast conductancy 4 to 6,000 feet, 60 cycle track circuit minimum ballast resistance per 1,000 feet, 4 ohms, 2 ohms, and 1 ohm. The relay end of quarter for 2, 4, and 2 ohms, and 1 ohm, 1/8 of an inch, and half blocks at length 4 and half the block length is 1/2 at 4 to 2 ohms, and trains end at 1/4 inch for 4 to 2 ohms, while the other 1 ohm goes between 1/8 of the relay end, 1/4 of the quarter block end, 1/4 of the 1/2 block end, and 1/4 of the 3/4 block end, and 1/8 of the trains end. For example, if it is desired to set up a 1 ohm per 1,000 feet ballast resistant condition on a 55,000 foot block having the day of the testing ballast resistant with 10 ohms per 1,000 feet, the total actual conductancy of the track circuit is 5/10^05 moh, which is reverse. It's kind of the reverse of the other side of the track circuit. The reverse of the ohm, so basically it's an ohm. Whether the conductancy desired with the 5 moh is, the additional conductancy will be the 5 minus the 0.5 to 4.5 moh. The conductancy should be divided in 5 parts, with the 3 of 1.123 moh, or a 0.89 ohms, and 2 of 563 moh and ohms, or 1.78 ohms. The 3089 ohm resistor should be placed across the rails at 1,250 feet, 2,500 feet, 3,750 feet from the relay end of the circuit, and the 1.78 ohm resistors should be placed on each of the cross of the relay transformer end of the track circuit. And part of this subject matter with the figures with reference to the chapter reproduced with the courtesy permission of the Union Switch Signal Company from copyrighted alternating current signal by the H. McCready. This was American Railway Signal Principles and Practices, Chapter 11, Non-Coded Alternating Train Circuits, October 1951, published in Signal Section AAR 59, East Van Buren Street, Chicago 5, Illinois.